Fade in. The camera drifts languidly across the cosmic ocean, a vast and silent graveyard where the remnants of collapsed stars linger like forgotten monuments. Nebulae shimmer faintly in the distance, their ethereal glow casting long shadows over the debris of stellar cataclysms, dense cores that once burned with the fury of creation, now reduced to enigmatic voids. The scene unfolds with deliberate slowness, each frame heavy with the weight of eons, as if the universe itself pauses to contemplate its own ruins. At the edge of known physics, there are things that only pretend to be what they are not. There are shadows that mimic eternity, stars that whisper the language of death, and one of them is the Gravastar. Humanity's understanding of a black hole paints it as the ultimate cosmic predator, a region where a massive star, having exhausted its nuclear fuel, succumbs to its own gravity in a final inexorable collapse. Observations from gravitational wave detectors capture the ripples of such events, mergers of these entities sending tremors through spacetime, confirming their existence as points of no return. At their core lies a singularity, a place of infinite density where the laws of physics as described by general relativity break down entirely. Space and time warp into oblivion, curving so sharply that even light, the swiftest traveler, cannot escape the grasp once it crosses the boundary known as the event horizon. Telescopes imaging the silhouettes of these objects against the glow of surrounding matter reveal disks of superheated gas spiraling inward, their light bent and distorted, affirming the presence of immense gravitational wells at the hearts of galaxies. Yet, an undercurrent of unease stirs beneath this accepted portrait. What if that impenetrable darkness is merely an illusion, a veil drawn by the universe to conceal a deeper truth? What if the cosmos has orchestrated a grand deception, leading observers to believe in monsters that, in their most terrifying form, do not truly exist? Theoretical explorations, rooted in papers from archives of scientific preprints, propose alternatives that challenge the singularity's inevitability, suggesting that quantum effects or exotic states of matter intervene at the brink of collapse, reshaping the narrative of stellar demise. The tone deepens into a blend of awe and disquiet as the camera zooms toward one such shadowy form, its outline hazy against the starfield. We believe a black hole is where gravity ascends to infinity, where no light can flee its embrace, where the very fabric of physics unravels into nothingness. But what if it never truly forms? What if, at the precise moment of collapse, when a star's core compressed beyond endurance teeters on the edge of eternal compression, something else emerges in its stead? Something that halts just short of oblivion, preserving a fragile equilibrium against the void. This reflection invites a philosophical gaze upon the black hole's dual nature, not merely a scientific construct, but a profound symbol woven into the human spirit. It embodies the void at the terminus of stellar lives, where fusion's fire yields to gravity's cold dominion, mirroring metaphors of endings in myths and meditations alike. The collapse of massive stars, documented through supernova remnants scattered across the sky, evokes the finality of cycles, birth in nebula cradles, life in radiant splendor, death in crushing silence. Yet the concept of Gravastars disrupts this somber finality. Emerging from theoretical models proposed in the early 2000s, these entities suggest that the universe does not obliterate its creations outright. Instead, it may feign destruction, maintaining the outward appearance of annihilation while concealing a more intricate reality beneath. In this view, the cosmos engages in a subtle art of preservation, where apparent endings mask continuations, challenging observers to question the boundaries between reality and ruse. At the heart of this enigma lies the central question, posed with a suspenseful pause as the narration builds toward revelation. Could the most terrifying objects in the universe, those we call black holes, actually be hollow? Could they be cosmic shells, filled not with a devouring singularity, but with something stranger, a vacuum infused with energy, a quantum field pulsing with negative pressure, a star composed of nothing but the essence of space itself. Visualize the boundary, where the event horizon would gleam with a faint, ethereal glow. Hawking radiation, that quantum whisper of particles evaporating from the edge, detected indirectly through theoretical predictions. Waves of spacetime ripple and distort around it, bending starlight into arcs and lenses, as confirmed by images of galactic centers where matter orbits in frantic ellipses. To all external observers, it manifests identically to a black hole, an inescapable gravitational trap, devouring infalling matter and energy without remorse. Yet within this facade, there might lurk no singularity, no point of infinite compression where information vanishes and paradoxes proliferate. Instead, a false surface emerges, a thin shell of ordinary matter, its thickness vanishingly small, encasing an interior realm governed by exotic physics. This shell, as hypothesized in scientific literature, forms when collapsing stellar material encounters a phase transition, akin to water freezing into ice but on a gravitational scale. Quantum fluctuations amplify, preventing the core from shrinking to a point. Inside, a region of de Sitter space prevails, a vacuum state with positive cosmological constant, where energy exerts a repulsive force countering the inward crush. This negative pressure, drawn from models of dark energy that drive the universe's acceleration, stabilizes the structure, creating a bubble of sorts. Matter approaching this boundary does not plunge into oblivion. It encounters a barrier where gravity, though immense, remains finite. No event horizon seals the fate irrevocably. Instead, a gravitational condensate mimics its effects, trapping light and matter in a dance at the precipice. Speculatively, yet grounded in extensions of these theories, such objects could nest within one another, like layers of a cosmic doll, each shell enclosing another in a hierarchy of stability. Recent propositions from 2024 explore this stacking, where multiple boundaries form, each resisting collapse through balanced forces. This configuration resolves long-standing puzzles. The information paradox, where quantum mechanics demands preservation of data that classical black holes would erase, finds solace in a structure without true horizons. Gravitational waves from mergers, rippling across the cosmos and captured by interferometers on Earth, might carry subtle signatures distinguishing these shells from singularities, perhaps echoes or damped oscillations, revealing internal complexities, emotional. Resonance builds as the narration reflects on humanity's gaze into these depths. For over a century, since the equations of general relativity first predicted such entities, observers have peered into the abyss, naming it truth, a testament to nature's unforgiving logic. Telescopes and simulations have mapped their influence, supermassive versions anchoring galaxies, their growth traced through quasar emissions billions of years old, stellar mass ones born from supernova blasts, their remnants pulsing as neutron stars teeter on the edge. Yet in the Gravastar's shadow, this truth fractures into possibility. What if the darkness we dread is not a devourer but a guardian, a relic that shields the universe from its own extremes? The camera descends slowly into the dark, the starfield fading as the void envelops the frame, leaving only the faint distortion of light at the horizon's edge. For a century, we have stared into the abyss and called it truth. But perhaps what we've been looking at is an actor. A star that died not into a hole but into a deception, a Gravastar. In this lingering ambiguity, the cosmos whispers of hidden harmonies, where endings dissolve into eternal pretense, and the universe reveals itself not as destroyer, but as eternal illusionist. In the shadowed corridors of human thought, where equations danced like fireflies against the infinite dark, the quest to unravel the universe's deepest enigmas began with a solitary mind reshaping reality itself. In 1915, amid the tumult of a world at war, Albert Einstein unveiled his general theory of relativity, a profound reconfiguration of existence. No longer was space a passive backdrop, nor time an unyielding march. Together, they formed a supple fabric, spacetime warped by the presence of mass and energy. Imagine a vast sheet, taut and ethereal, dimpled by the weight of stars and planets guiding the arcs of comets and the fall of leaves in harmonious curves. Einstein's equations, elegant in their symmetry, predicted that under extreme conditions, when a massive star exhausted its nuclear fire and collapsed under its own gravity, the fabric could crumple inward, folding upon itself in a descent toward oblivion. This was no gentle bending. It hinted at realms where light itself might be ensnared, where the laws of physics strained against the pull of inexorable density. Yet Einstein, ever the philosopher, pondered the implications with a mix of awe and unease, for his theory whispered of boundaries where intuition faltered, edges of creation where the cosmos concealed its most guarded secrets. Scarcely a year later, in the quiet aftermath of Einstein's revelation, Karl Schwarzschild, a German physicist serving on the Eastern Front, derived the first exact solution to those formidable equations. Amid the echoes of artillery, he envisioned a spherical mass compressing spacetime to a critical radius, now bearing his name, the Schwarzschild radius. Beyond this horizon, no path led outward. Light rays bent inexorably inward, trapped in eternal loops. This mathematical construct described a region severed from the observable universe, an event horizon encircling a core of unfathomable compression. Schwarzschild's work painted a portrait of gravitational extremity, a star's corpse, imploded beyond recovery, where time dilated to a standstill for distant observers, and matter vanished into a point of infinite density, a singularity. Though Schwarzschild perished soon after from illness contracted in the trenches, his solution endured as a cornerstone, a theoretical sentinel guarding the gates of cosmic collapse. It suggested that the universe harbored voids not of emptiness, but of absolute finality, where the fabric of reality tore under its own weight. Reflectively, one senses in this discovery a philosophical undercurrent, the horizon as a veil, separating the known from the unknowable, inviting speculation on what truths might lie entombed within. Decades passed, like the slow drift of galaxies across the void, before these abstract curiosities coalesced into the cultural and scientific icon known today. In the mid-20th century, John Wheeler, an American physicist with a flair for metaphor, breathed life into the concept. During a 1967 conference, he christened these entities black holes, a term that evoked the abyssal maw of a cosmic predator, devouring light and matter alike. Wheeler's vision transformed Schwarzschild's mathematics into a dynamic narrative. Stars, after billions of years fusing elements in their hearts, succumbed to gravity's embrace, their outer layers exploding in supernovae, while cores plunged into darkness. He explored the no-hair theorem, positing that black holes retained only mass, charge, and spin, erasing all other traces of their progenitor stars, a cosmic amnesia. Wheeler's work bridged theory and observation. The discovery of quasars, distant beacons powered by accretion disks around supermassive black holes, lent empirical weight. Cygnus X1, identified in the 1970s as a likely black hole binary, further anchored the idea in reality. Philosophically, Wheeler's black holes embodied mystery incarnate, portals to extremes where gravity triumphed over all forces, challenging humanity's grasp on finitude and infinity. Yet even as they captivated, they sowed seeds of doubt. What lurked at the singularity's heart, where equations diverged to absurdity? As the 20th century waned, casting long shadows over established paradigms, physicists began to probe the fissures in black hole theory with increasing scrutiny. Observations mounted. The Event Horizon Telescope's 2019 image of M87's shadow, a ring of light bent around an unseen void, affirmed their existence. Yet theoretical tensions simmered. General relativity, masterful in describing large-scale gravity, clashed with quantum mechanics, the realm of the subatomic. At the singularity, densities soared to infinities, volumes shrank to zero, aberrations that quantum principles abhorred, insisting on probabilistic waves and finite limits. Stephen Hawking's 1974 revelation of black hole evaporation, where quantum fluctuations near the horizon birthed particle pairs, one escaping as radiation while the other fell inward, deepened the paradox. Black holes, it seemed, could shrink and vanish, but what of the information encoded in the infalling matter? Quantum mechanics demanded its preservation. Relativity suggested its obliteration. This information paradox gnawed at the foundations, hinting that singularities might be illusions, artifacts of an incomplete theory. Speculatively, credible avenues emerged. String theory's holographic principle, projecting the universe's contents onto lower dimensional surfaces, or loop quantum gravity, discretizing space-time into loops averting infinities. These whispers suggested that before collapse reached singularity, quantum effects might intervene, rewriting the narrative of gravitational demise. Into this ferment of doubt stepped Pavel Mazur and Emil Motola, two theorists whose 2001 proposal ignited a subtle revolution. Drawing from the quantum vacuum's restless energy, fluctuations birthing virtual particles in empty space, they envisioned an alternative to the black hole's fatal plunge. Their paper, grounded in general relativity augmented by quantum considerations, introduced the gravitational vacuum star, or Gravastar, a compact object born from stellar collapse but halted at the brink. As matter compressed toward the Schwarzschild radius, they argued, a phase transition occurred, akin to water freezing into ice under pressure. The interior transformed not into a singularity, but into a bubble of de Sitter space, a region dominated by positive vacuum energy, repulsive like the dark energy accelerating the universe's expansion. This inner void, stable against further collapse, was encased in a thin shell of ultra-dense matter, where quantum gravity effects condensed energy into an exotic phase, balancing the inward pull. From afar, the Gravastar mimicked a black hole. Its gravity warped light identically. Accretion disks swirled the same, yet it lacked an event horizon. Light could graze perilously close, but no true trap existed. Instead, a surface, albeit Planck-scale thin, reflected or absorbed in ways black holes could not. Mazur and Motola's model resolved the singularity's infinities by replacing them with a quantum-stabilized vacuum, where negative pressure counteracted gravity's crush. Credibly extending this, one might speculate that the shell arises from Bose-Einstein condensation of gravitons, quantum carriers of gravity, forming a coherent state resistant to collapse, echoing condensates in ultra-cold laboratories. The proposal drew from cosmological constants, observed in the universe's flat geometry and dark energy's dominance, suggesting Gravastars as microcosms of cosmic repulsion. Philosophically, it evoked a cosmos of balance. Where black holes symbolized irreversible loss, Gravastars hinted at resilience, a universe that abhorred absolutes, preserving information on their surfaces much like holograms. Yet the idea landed in a landscape skeptical of alternatives. Black holes, bolstered by gravitational wave detections from LIGO in 2015 onward, ripples from mergers matching relativity's predictions, seemed unassailable. Critics dismissed Gravastars as contrived, requiring fine-tuned conditions, their stability unproven against perturbations. Despite this chill reception, the Gravastar hypothesis lingered like a specter in the halls of theoretical physics, refusing entombment. In the ensuing decades, it found quiet champions who refined its contours. By the mid-2010s, explorations in modified gravity theories, such as FR extensions of relativity, modeled Gravastars with enhanced stability, their shells resisting quantum decay. Observational tests emerged, If gravastars possessed reflective surfaces, mergers might produce gravitational wave echoes, delayed reverberations absent in black holes. Searches in LIGO-Virgo data, initiated around 2016, scanned for these signatures. While initial claims stirred debate, rigorous analyses found no conclusive evidence, yet the possibility endured, fueling proposals for future detectors like LISA, set to launch in the 2030s, to probe lower frequencies where echoes might resonate clearer. Speculatively, credible interpretations linked gravastars to wormholes or baby universes, where the inner de Sitter space connected to alternate realms, bridging quantum foam's topology. As the 2020s unfolded, the hypothesis gained traction amid broader quests for quantum gravity. Papers in 2024 proposed nested gravastars, akin to Matryoshka dolls, with layered shells balancing dark energy tensions, offering greater equilibrium than singular structures. Integrations with string clouds, hypothetical one-dimensional defects from symmetry breaking, and quintessence fields, dynamic dark energy variants, yielded models where gravastars influenced cosmological evolution, perhaps seeding galaxy clusters. By 2025, investigations in rastral gravity, a non-conservative extension emphasizing matter curvature coupling, and mimetic gravity, mimicking dark matter through scalar fields, constructed gravastar interiors resilient to entropy buildup, addressing Hawking's paradox by externalizing information, modified Gauss-Bonnet gravity, incorporating higher dimensional curvatures, analyzed gravastar entropy and stability, revealing lower thermodynamic fluctuations than black holes, hinting at observational distinguishability via shadow asymmetries in future telescopes. These advancements, drawn from archival repositories like Archivint, underscored the gravastar's evolution from outlier to viable contender. In Kuchowicz spacetime, a generalized metric for anisotropic fluids, recent models depicted gravastars with radial pressures sustaining shells against collapse. Their equations of state-echoing neutron stars, yet amplified by vacuum contributions. Philosophically, this persistence mirrors the universe's own enigmas, dark energy, comprising nearly 70% of existence, remains elusive, its repulsive nature paralleling the gravastar's core. Could gravastars be manifestations of this cosmic force, compact laboratories for unification? Reflectively, the intellectual lineage, from Einstein's curved spacetime, through Schwarzschild's horizon and Wheeler's nomenclature, to Mazur and Motola's vacuum rebirth, traces an arc of human ingenuity confronting the void. Black holes, once unchallenged, now share the stage with this ghostly alternative, a hypothesis that whispers of hidden harmonies, where infinities yield to quantum grace. In the quiet suspense of ongoing inquiry, the gravastar endures as a philosophical beacon, a reminder that the universe's deepest truths may not lie in destruction, but in transformation. As detectors listen for echoes and theorists weave new metrics, the mystery deepens. What if the shadows we observe are not holes, but stars reborn in vacuum's embrace? This lineage, forged in equations and speculation, invites eternal reflection on reality's fabric, where collapsed births not end, but a new equilibrium in the cosmic dance. In the shadowed depths of the cosmos, where the fabric of space-time bends to the will of immense gravity, a revolutionary idea emerges to unsettle the foundations of understanding. The Gravastar, a hypothetical construct born from the equations of general relativity, dares to challenge the sanctity of the black hole's event horizon, that invisible veil marking the boundary of no return. For decades, the event horizon has stood as a cornerstone of Einstein's vision, a threshold where light and matter plunge into oblivion, their fates sealed within an inescapable grip. Yet the Gravastar whispers of an alternative reality, one where this point of no escape is but a mirage, a deceptive layer concealing a stable core rather than an abyss of infinite density. This proposition strikes at the heart of cosmic paradigms, suggesting that the universe may abhor the infinities long attributed to black holes, opting instead for elegant resolutions hidden in quantum whispers. Consider the black hole, that enigmatic sentinel forged in the collapse of massive stars. When a star exhausts its nuclear fuel, gravity asserts dominance, compressing the core beyond the resilience of atomic structures. Electrons, once repelling one another in white dwarfs, yield to degeneracy pressure's limits. Neutrons, in their dense packing within neutron stars, reach a threshold around 3 times the Sun's mass. Beyond this, collapse seems inevitable, space-time curving so profoundly that a critical radius forms, the Schwarzschild radius, named after the physicist who first derived it from Einstein's field equations. Within this radius, the escape velocity exceeds the speed of light, birthing the event horizon. Matter and radiation crossing this boundary vanish from the observable universe, their information seemingly erased, funneled toward a central singularity where density becomes infinite and the laws of physics fracture. This narrative, supported by observations of stellar remnants and galactic centers, has endured since the early 20th century. Telescopes detect the gravitational lensing around these objects, where light from background stars warps in telltale arcs. Gravitational waves, those ripples in spacetime detected by interferometers since 2015, chronicle the mergers of these compact entities. They're in spiral and ring-down phases, aligning with predictions of general relativity. Images from horizon-scale telescopes, capturing the photon rings around supermassive candidates at the hearts of distant galaxies, further cement the black hole's reality. Yet beneath this empirical veneer lies a profound discord, a clash between the smooth determinism of relativity and the probabilistic essence of quantum mechanics. The tension crystallizes in the information paradox. Illuminated by a physicist's seminal work in the 1970s, Stephen Hawking, merging quantum field theory with the curved spacetime near a black hole's horizon, revealed a startling process. Virtual particle pairs, born from the vacuum's quantum fluctuations, could be torn apart by tidal forces. One particle falls inward, while its partner escapes as thermal radiation, carrying away energy and gradually eroding the black hole's mass. Over eons, vast timescales for stellar mass objects, shorter for minuscule ones, this evaporation would consume the entity entirely, leaving only a diffuse glow. But herein lies the heresy. If the radiation is purely thermal, devoid of specifics about the infallen matter, then information, the quantum states encoding what fell in, is destroyed. Quantum theory's unitarity, the principle that information must be conserved, preserved through reversible evolutions, stands violated. The universe in this view permits irreversible loss, a philosophical affront to the predictability of physical laws. Hawking's calculation, grounded in semi-classical approximations, sparked decades of debate. Attempts to resolve the paradox invoke holography, where information resides on the horizon's surface like a two-dimensional projection, or firewalls, hypothetical barriers of high-energy particles at the horizon that challenge the equivalence principle. Yet these solutions strain the seams of established theories, leaving physicists to grapple with the irreconcilable. Relativity's horizons demand isolation, while quantum mechanics insists on entanglement and preservation. The paradox endures, a shadow over the black hole's throne, hinting that the event horizon may not be the immutable barrier it appears. Into this void steps the Gravastar, proposed in 2001 by theorists Pavel Mazur and Emil Mottola as a radical reconfiguration of collapsed matter. Drawing from the same Einstein field equations that birthed black holes, the Gravastar eschews the singularity and horizon altogether. Imagine a star's core in its final throes, undergoing a phase transition akin to water freezing into ice. But here, the transition involves quantum gravitational effects. The interior transforms into a de-Sitter space, a region dominated by a positive cosmological constant, where vacuum energy repels rather than attracts. This false vacuum, with negative pressure balancing the inward crush, forms a stable bubble-like core of constant density, preventing infinite collapse. Surrounding it is a thin shell, mere Planck lengths thick, on the scale of the smallest quantum distances, composed of ultra-relativistic fluid, matter behaving as if at near light speeds, its pressure equaling its energy density. This shell, perched just outside what would be the event horizon in a black hole, acts as a membrane, radiating quantum noise outward while containing the interior's expanse. From afar, the Gravastar's gravitational field mirrors that of a black hole. The exterior metric remains Schwarzschild, curving spacetime identically, drawing in matter with the same inexorable force. Light orbits at the same photon sphere, 3/2 the critical radius, casting shadows indistinguishable from those imaged in recent observations. Yet crucially, no true horizon forms. The shell permits a faint leakage, a subtle echo where information might persist rather than perish. Hawking-like radiation emerges not from pair production at a one-way boundary, but from the shell's quantum excitations, potentially encoding the influent data in correlated emissions, thus upholding unitarity without invoking paradoxes. Theoretical refinements have evolved this concept. Early models faced stability concerns, particularly for rotating configurations, where centrifugal forces might disrupt the shell. Subsequent analyses, incorporating quantum corrections and modified gravity frameworks, suggest pathways to equilibrium, the shell's exotic matter, with equation of state violating classical energy conditions, yet permissible in quantum realms, could sustain against perturbations. Recent explorations, published in archival repositories as late as 2025, extend Gravastars to higher dimensions or alternative geometries, such as thin shell variants in three-dimensional spacetimes with minimal length scales imposed by quantum gravity. These models incorporate modified Gauss-Bonnet terms, curvature invariants that alter gravity at high energies, potentially stabilizing the structure against collapse while influencing entropy and energy distributions. One intriguing development posits nested Gravastars, or nestars, resembling matryoshka dolls of gravitational condensate. Proposed in 2024 and refined thereafter, this layered architecture features a smaller Gravastar embedded within a larger one, each shell balanced by interior vacuum energy. Such nesting enhances stability, as inner layers counterbalance outer tensions and aligns gravitational wave signatures more closely with observed mergers. During collisions, the ring-down phase, the oscillatory settling after inspiral, might exhibit subtle echoes, delayed reflections from the shells, distinguishable from the clean quasi-normal modes of black holes. While current gravitational wave detections favor the latter, future observatories with heightened sensitivity could probe these nuances, seeking deviations in the waveform tails. The Gravastar's allure lies in its resolution of the information paradox without abandoning core principles. Absent a horizon, causality remains intact. No firewall scorches infalling observers. No singularity mocks finite descriptions. Information, imprinted on the shell's quantum states, could radiate gradually, entangled pairs preserving the original data in a holographic dance. This speculative yet credible interpretation, supported by analogies to Bose-Einstein condensates, where acoustic horizons mimic gravitational ones, suggests that the universe favors continuity over erasure. Laboratory experiments with ultra-cold atoms have demonstrated Hawking-like radiation at fluid interfaces, hinting that similar mechanisms might operate at cosmic scales, bolstering the Gravastar's theoretical footing. Yet the paradigm shift extends beyond mechanics to the emotional and philosophical realms. If Gravastars prevail, the notion of cosmic death transforms. Stars in their senescence do not succumb to violent implosion and eternal silence. They metamorphose into serene orbs, their essence preserved in a quantum equilibrium. The light they once emitted, the matter they accreted, lingers not in oblivion but in a stable repose, a testament to nature's aversion to waste. This reimagining evokes a universe of subtle mercy, where endings are transitions, infinity's illusions crafted by incomplete theories. The singularity, that point of mathematical despair, dissolves into a finite core, space-time's integrity restored. The unsettling truth amplifies the mystery. No instrument yet devised can pierce the veil between Gravastar and black hole. The shadows cast by supermassive entities at galactic cores, the accretion disks flaring with X-ray bursts, the gravitational waves from distant mergers, all conform to both models. Even the faint Hawking radiation too dim for current detection, might manifest similarly, its spectrum thermal yet subtly modulated. Proposals for distinction hinge on future precision. Echoes in gravitational wave ringdowns, polarization patterns in infalling light, or deviations in orbital dynamics of nearby stars. So until then, ambiguity reigns. The cosmos may harbor pretenders, objects masquerading as black holes while harboring secrets of stability. Reflect on this cosmic sleight of hand. What if the universe, in its profound wisdom, never permits true infinities? The event horizon, that supposed sentinel of loss, becomes a permeable threshold, a quantum facade where collapse halts at the brink. Every apparent end, the dimming of stars, the merging of masses, reveals itself as an illusion, a perceptual trick born from distant vantage. In this light, the information paradox dissolves not through contorted amendments, but through elegant redesign, the laws of physics harmonizing in a symphony of preservation. The Gravastar, though unproven, invites contemplation of a reality where nothing is truly forsaken, where the fabric of existence weaves continuity from the threads of potential catastrophe. As telescopes scan the heavens and detectors listen to spacetime's murmurs, the shock persists. The black hole, icon of cosmic extremity, may yield to a gentler archetype, one that echoes the universe's preference for balance over breakdown. In the quiet aftermath of stellar demise, stability endures, a silent guardian against the void. The narrator's voice, hushed in reverence, poses the eternal query. In a cosmos that remembers its origins, might every collapse conceal a rebirth, every darkness a hidden light? The Gravastar, poised at the edge of theory and observation, beckons toward this profound re-evaluation, where the death of light is but a prelude to enduring mystery. In the hushed corridors of observatories, perched on mountain peaks and in the digital realms, where equations dance like shadows on cave walls, scientists embarked on a quest to pierce the veil of the Gravastar hypothesis. This enigmatic alternative to black holes, born from the minds of theorists seeking to resolve the paradoxes of singularities, demanded scrutiny, not through mere speculation, but through the unyielding lens of observation and the rigorous forge of theory. Gravastars, those hypothetical spheres where gravity's crush halts at a quantum threshold, promised a cosmos without the infinite densities that defy reason. Yet to affirm their existence, or to relegate them to the realm of elegant illusions, required evidence etched in the fabric of space-time itself. The pursuit unfolded slowly, a symphony of data streams and mathematical whispers, building toward revelations that blurred the line between the seen and the concealed. The journey began with the gaze of a global network of radio telescopes, synchronized like a planetary orchestra, to capture the silhouette of what many deemed a black hole at the heart of the galaxy Messier 87. In 2019, this collaboration unveiled the first direct image, a luminous ring encircling a profound darkness, a void where light bent and faltered. The portrait, assembled from signals gathered across continents, depicted not the object itself but the dance of photons around its boundary. Here, gravity warped space-time so severely that light orbited in unstable paths, forming a bright halo against the cosmic night. Yet, as astronomers contemplated this ethereal glow, a question lingered like mist over a forgotten lake. What truly lay within that shadowed core? The image revealed only the exterior drama, the accretion disk's fiery turmoil, the magnetic fields twisting plasma into jets that pierced the void. The interior remained an enigma, shrouded beyond the reach of even the most piercing instruments. Could this radiant boundary conceal not a black hole's inescapable horizon, but the quantum membrane of a Gravastar? In theoretical models, Gravastars possess no true event horizon, that one-way threshold from which nothing returns. Instead, they feature a thin shell, a barrier forged from quantum effects where matter's density surges to extremes, resisting collapse. Photons grazing this edge would trace similar paths, yielding a shadow indistinguishable from a black hole's at first glance. The bright ring, that iconic crescent of amplified light, might thus be the signature of a false horizon, a surface where gravity's pull meets its match in exotic pressures. Theorists, drawing from general relativity modified by quantum corrections, posited that the image's subtle asymmetries could hint at deviations, perhaps a faint blurring or an unexpected polarization, whispers of a structure sustained by vacuum fluctuations rather than oblivion. Yet the data, while revolutionary, offered no definitive verdict. It was a canvas of ambiguity, inviting speculation that these cosmic behemoths might be gravastars in disguise, their true nature veiled by the very light that outlined them. The suspense deepened. If gravastars existed, they would mimic their darker counterparts so convincingly that only finer probes could unmask them. Turning from the static portraits of distant giants, scientists sought dynamical signatures in the ripples of space-time itself, gravitational waves, those undulations born from the universe's most violent unions. Detectors, vast interferometers stretching arms across landscapes in the United States, Italy, and beyond, listened for the cosmic tremors of merging compact objects. Since their first detection in 2015, these instruments had chronicled dozens of collisions, stellar remnants spiraling inward, their orbits decaying in a chirp of increasing frequency, culminating in a merger's ringdown, a fading hum as the newborn entity settled into equilibrium. The waveforms, plotted as strains in the fabric of space, matched predictions from general relativity with exquisite precision, affirming the presence of horizons that swallowed information whole. But in the Gravastar paradigm, such mergers would unfold differently, subtly yet profoundly. Lacking true horizons, Gravastars would not ring like perfect bells, but echo like caverns disturbed by a stone's fall. In the aftermath of fusion, gravitational waves trapped near the shell might bounce repeatedly, leaking out as faint, delayed signals, echoes that black holes, with their absorbing boundaries, could never produce. These reverberations, spaced by the time light takes to traverse the object's radius, would manifest as periodic modulations in the tail of the waveform, a ghostly afterimage of the merger's violence. Theorists modeled these scenarios using perturbation theory, simulating how waves propagate in spacetimes with reflective surfaces. The differences were minute, buried in noise yet detectable in principle with sufficient sensitivity. As data accumulated from observing runs, analysts sifted through the signals, hunting for these elusive echoes that could betray a Gravastar's presence. Among those leading this charge was physicist Vitor Cardoso, whose work illuminated the potential of gravitational waves as probes of exotic matter. In papers exploring alternatives to black holes, Cardoso and collaborators demonstrated that objects like gravastars or wormholes would generate echo trains, series of pulses modulated by the structure's properties, echoing across the detector's baselines. Analyzing early merger events, some researchers reported intriguing anomalies, subtle deviations in the ringdown phase, hints of repetition that aligned with echo models. These findings, published in theoretical journals and debated at conferences, stirred the community. Yet they remained inconclusive, shadowed by statistical uncertainties and alternative explanations, perhaps mere artifacts of detector noise or unmodeled astrophysical effects. Subsequent observations, bolstered by upgraded instruments and international partnerships, refined the search. By 2025, catalogues of over 200 detections offered a richer data set, yet the echoes eluded confirmation. The tension mounted. Were these absences evidence against gravastars or simply the limits of current technology? The waveforms, like ancient scrolls partially eroded by time, held secrets that demanded ever sharper tools to decipher. Delving deeper into the theoretical underpinnings, scientists constructed quantum field models, to envision the Gravastar's interior, a realm where vacuum energy reigns supreme. In the quantum vacuum, particles flicker in and out of existence, their fleeting lives contributing a sea of energy that permeates space-time. For Gravastars, this vacuum condensate forms the core, a stable bubble where negative pressure, akin to that of a cosmological constant, counteracts gravitational collapse. Drawing from effective field theories that blend gravity with quantum mechanics, models depicted the interior as a de Sitter space, a positively curved expanse driven by this repulsive force. Here the energy density remains constant, exerting an outward push that halts the infill of matter at a finite radius. No singularity forms. Instead, the core expands eternally within its confines, a microcosm of cosmic inflation frozen in miniature. Outside this bubble, space-time reverts to the familiar Schwarzschild geometry, indistinguishable from a black hole's exterior. The transition occurs at a razor-thin shell, where quantum gravity effects dominate. Matter density here approaches the Planck scale, that fundamental limit where lengths shrink to 10⁻⁵ meters, and quantum fluctuations warp reality itself. In this regime, general relativity yields to speculative frameworks like loop quantum gravity or string theory, where space-time emerges from discrete loops or vibrating strings. The shell, a phase boundary between classical and quantum domains, sustains itself through these effects, preventing horizon formation. Simulations on supercomputers, grounded in equations from quantum field theory on curved backgrounds, explored stability. Perturbations ripple across the surface but dampen, preserving the structure against collapse or explosion. This delicate balance evoked a profound reflection, the Gravastar as a testament to nature's aversion to infinities, a harmonious resolution to gravity's extremes. This architecture forged a tantalizing link to one of cosmology's greatest riddles, dark energy and the cosmological constant problem. Dark energy, that ethereal force accelerating the universe's expansion, manifests as a positive cosmological constant in Einstein's equations, a vacuum energy density far smaller than quantum predictions suggest. The discrepancy spans 120 orders of magnitude, a chasm that haunts theorists. In Gravastar models, the interior's negative pressure mirrors this dark energy, stabilized by the same vacuum contributions. Some speculations drawn from Arcshift preprints propose that Gravastars could embody localized pockets of this energy, their shells channeling quantum corrections to match observed values. Perhaps the cosmological constant arises from an ensemble of such objects, their collective influence permeating the cosmos. More audaciously, the force driving universal expansion might also underpin these stellar remnants, rendering Gravastars as tiny universes unto themselves, each encapsulating its own vacuum energy, insulated from the broader expanse. The philosophical undercurrent swelled like a tide beneath these inquiries, eroding the distinctions between object and universe. Gravastars in their essence blurred these boundaries, compact yet expansive within. They resembled bubbles of space-time sealed off by quantum membranes. Were they mere remnants of stellar death, or cosmic microcosms, each a self-contained realm where time and space unfolded independently? Theoretical extensions imagined nested structures like Russian dolls of gravity, Gravastars within Gravastars, layers of vacuum energy stacked in fractal harmony. In such visions, grounded in solutions to Einstein's equations with multiple shells, the innermost cores might harbor their own laws, their own evolutions, forever hidden from external observers. The event horizon's absence meant no information loss paradox. Instead, the shell preserved records, a quantum archive of infallen matter. This notion evoked a mysterious solitude, each Gravastar as a private cosmos, adrift in the greater void, its interior a sanctuary untouched by the outer world's gaze. Photons and particles skimming the surface might carry faint imprints, but the heart remained inviolate, a realm where dark energies whisper sustained eternal equilibrium. Reflecting on this, one pondered the universe's architecture. If black holes were illusions, replaced by these resilient spheres, then existence itself might be a mosaic of isolated domains, connected only by gravity's subtle threads. The search for echoes, the scrutiny of shadows, became more than scientific endeavor. It was a meditation on isolation and unity, on the hidden depths that define reality. As data from telescopes and detectors accumulated, the Gravastar hypothesis lingered in the twilight between possibility and refutation. No conclusive proof emerged, yet the models endured, refined by quantum insights and observational constraints. In this ongoing narrative, the cosmos revealed itself not as a collection of certainties, but as a tapestry of enigmas, where the boundary between the known and the concealed invited eternal contemplation. The bright ring of Messier 87, the fading chirps of mergers, these were portals to deeper truths, echoes of a universe that, in its quiet defiance of collapse, whispered of infinities tamed and memories preserved in the quantum foam. In the lingering hush where light succumbs to the void and reality teeters on the brink of perception's absence, another layer of enigma unfolds. The colossal entities once deemed black holes, those devourers of light and architects of gravitational tyranny, now whisper of deception. As theorists refine their models of these gravitational vacuum stars, or Gravastars, the constructs grow ever more peculiar, defying the simplicity of collapse into nothingness. These hypothetical behemoths, born from the same stellar cataclysms that forge black holes, emerge not as singularities piercing the fabric of spacetime, but as stable spheres enveloped in a thin shell of exotic matter, enclosing a bubble of de Sitter vacuum where pressures counterbalance the inward crush. The more equations are solved, the stranger the implications. Exteriors that mirror black holes in every observable trait, yet interiors that rewrite the rules of existence, challenging the very notion of finality in the cosmos. Picture the formation, drawn from the rigorous calculations of general relativity, extended to quantum corrections. A massive star, its core depleted of fusion's fire, succumbs to gravity's inexorable pull, compressing inward. In the classical view, this leads to a singularity, a point of infinite density where physics falters. But in the Gravastar paradigm, proposed in the early 21st century as a resolution to paradoxes plaguing black holes, quantum effects intervene. A phase transition occurs, akin to water freezing under pressure, transforming the collapsing matter into a thin, rigid shell. This shell, mere plank lengths thick, yet imbued with negative pressure, halts the plunge, surrounding an interior dominated by a positive cosmological constant, a vacuum energy that repels, maintaining equilibrium. Theoretical models, refined through decades of numerical simulations, show these structures stable against perturbations, their oscillations damping like ripples on a serene pond, rather than amplifying into catastrophe. The exterior spacetime bends identically to that of a black hole. The same mass warps orbits, the same spin twists frames, the same gravitational lensing distorts the light of distant stars into ethereal arcs. Hey, observers from afar, armed with telescopes capturing the infrared glow of accretion disks or the radio whispers of event horizons, would discern no difference. Yet this mimicry conceals a profound divergence, for within lies no abyss, but a preserved realm where information endures, uncrushed by infinity. The absence of a singularity alters everything, unraveling the interior physics in ways that echo through the foundations of time and causality. In a black hole beyond the event horizon, the geometry inverts. Radial distance becomes time-like, time space-like, compelling all paths to converge inexorably toward the singularity. Matter and light, once fallen, march forward in what was space, but now is an irreversible temporal flow, erasing distinctions between future and fate. This swap, derived from the Schwarzschild metric and its rotating Kerr extensions, enforces a one-way journey where causality bends to gravity's will, and the past's echoes are silenced in the crush. Gravastars, however, eschew this inversion. Their thin shell, a boundary of ultra-dense matter with equation of state P sequence R, acts as a membrane, separating the exterior's familiar spacetime from an interior where de Sitter geometry prevails, a space of constant positive curvature, expanding under vacuum energy. Here time proceeds unwarped, causality intact, as if the collapse never breached the quantum threshold. Speculatively, yet credibly grounded in the mathematics of matching interior and exterior solutions, this bubble could harbor a frozen universe, particles suspended in a stable configuration, their interactions mediated by fields that persist without the singularity's erasure. The interior, insulated from the outside, might evolve on timescales dilated to eternity for external observers, a pocket of reality where the star's final moments linger, preserved like amber encasing ancient forms. This reconfiguration invites deeper contemplation on the interplay of time and causality across cosmic scales. In black holes, the horizon enforces no escape. Information seemingly lost to the singularity, fueling debates over conservation laws. Gravastars resolve this by design. The shell encodes all infalling data on its surface, much like a holographic projection, allowing radiation to carry it away without paradox. Time within flows linearly, causality unchallenged, permitting hypothetical traversals, though none could cross the shell without exotic energies. Recent theoretical advancements, such as constructions linking regular black holes to thin-shell gravastars, demonstrate how these models satisfy energy conditions while avoiding naked singularities, ensuring stability under axial and polar perturbations. The sound speed on the shell approaching that of light maintains causal structure, preventing a causal loops. Yet the mystery swells. If such interiors exist, they could seed new realms where the vacuum's expansion mimics an inflationary epoch, birthing structures unseen from our vantage. The cosmos, in this view, becomes a labyrinth of nested times, where each gravastar cradles a timeline insulated, yet intertwined with the greater whole. Speculation, anchored in these credible extensions, beckons toward audacious horizons. Consider the Big Bang, that primordial explosion from which all emerged, a singularity in reverse, expanding from infinite density. Could it have originated as the interior of a collapsing star in a parent universe, a gravastar whose shell burst or transitioned, unleashing its de Sitter bubble into our reality? Theoretical explorations, drawing from eternal inflation and bubble nucleation models, posit that quantum tunneling through gravitational barriers could spawn daughter universes within such structures. The de Sitter vacuum, with its exponential growth, mirrors the rapid inflation observed in our cosmos's early moments, evidenced by the uniformity of the microwave background and the flatness of spacetime. If the Big Bang were the release from a gravastar's core, it would imply a cyclic or multiversal genealogy, where collapses in one realm seed births in another, preserving information across boundaries. Extending this, every apparent black hole in our universe might conceal a gravastar, its interior a nascent cosmos, planets, stars, perhaps intelligences, evolving in isolation. This fractal chain, realities nested within realities like infinite reflections in opposing mirrors, emerges from the mathematics of asymptotic flatness and de Sitter matching. Each layer encodes the previous, a holographic recursion where the universe's memory fractalizes, eternal and self-similar. The philosophical resonance deepens, existence as a cascade of veils, each lifting to reveal not void, but vaster depths. The tension escalates as observational data trickles in from the frontiers of astronomy, subtle discrepancies gnawing at the black hole paradigm. Gravitational wave observatories, their laser arms stretching kilometers to detect spacetime's tremors, have chronicled mergers of these titans, ripples from binary dances that spiral into unity. Yet amid the expected chirps and ringdowns, echoes linger. Faint repetitions in the waveforms suggested in analyses of events from 2015 onward, though debated as noise or artifacts. Recent detections, including anomalies in the gravitational wave background, a low-frequency hum from supermassive pairings, reveal unexpected hotspots and deviations, as reported in 2024 studies. These could stem from the cavity resonances of Gravastars, wherein falling waves bounce between the photon sphere and the shell, producing delayed pulses absent in singular black holes. Theoretical predictions align. For a 60 solar mass Gravastar, the fundamental mode's frequency scales with compactness, damping over milliseconds, detectable by advanced instruments. Space telescopes, peering in infrared to unveil the universe's youth, uncover brightness fluctuations in quasars, active nuclei thought powered by black holes, inconsistent with standard accretion models. Early 2020s observations of unexpectedly massive entities in the cosmic dawn hint at formation mechanisms bypassing singularities, perhaps Gravastar precursors stabilizing rapidly. Radio telescope arrays, imaging the shadows of these behemoths through very long baseline interferometry, capture silhouettes around galactic centers. The 2019 and 2022 images show rings of light encircling darkness, yet subtle asymmetries and emission profiles deviate slightly from Kerr predictions. Shadow diameters fractionally larger, brightness depressions less pronounced. Papers from 2023-2024, simulating Gravastar shadows via general relativistic magnetohydrodynamics, find that thin shells yield images with muted photon rings, aligning better with some data points while ruling out thicker variants. These anomalies, accumulating like whispers in a gathering storm, could be mere coincidences, statistical flukes or instrumental quirks, or harbingers that the cosmos has cloaked its true nature in black hole guise. As the evidence mounts, the emotional undercurrent surges, a quiet turmoil reflecting humanity's gaze into the abyss. The universe, once a recorder of indelible memories, now reveals itself as a master of illusion, where the apparent voids pulse with hidden vitality. The deeper scrutiny penetrates these shadows, through waves that echo unresolved, luminosities that flicker anomalously, silhouettes that hint at unseen structures. The more the darkness reciprocates, not as an empty maw devouring all, but as a translucent shroud concealing infinities. In this veiled gaze, the cosmos confronts its observers with a mirror of their own ephemerality, fleeting beings deciphering an eternal puzzle where each revelation peels back layers only to expose deeper mysteries. Gravastars, in their strange elegance, embody this duality, mimics of oblivion yet bastions of preservation, interiors teeming with potential universes, time flowing unhindered amid the crush. The fractal nesting evokes a profound interconnectedness, our reality perhaps a bubble within another's collapse, memories cascading through dimensions, causality a thread binding the chain. Yet the anomalies persist, urging a re-evaluation, gravitational, echoes that might confirm the shell's resonance, infrared fluctuations signaling internal stability, radio shadows betraying the absence of horizons. Speculatively, if these hints solidify, the universe transforms from a collection of isolated singularities into a web of nested existences where information not only endures but proliferates, birthing new realms from the old. This escalation propels the narrative toward uncharted territories where the philosophical weight bears down. Time in Gravastars escapes the black hole's tyranny, allowing causal chains to persist within, perhaps fostering evolutions parallel to our own. The De Sitter interior, with its anti-gravity-like expansion, could mimic the dark energy driving. Our cosmos's acceleration, suggesting a symmetry between micro and macro scales. Theoretical models extending to higher dimensions, incorporating Gauss-Bonnet terms, further stabilize these constructs, implying viability in modified gravities. Observational tensions heighten post-merger echoes in gravitational waves, predicted at kilohertz frequencies, await detection by next-generation arrays. Shadow tests requiring microarc-second resolutions loom on the horizon of technological advance. The Big Bang's echo in this framework resonates deeply. A Gravastar in a predecessor universe, its shell yielding to quantum fluctuations, inflating into our expanse. The nested universe's hypothesis, while speculative, draws credence from string theory landscapes where vacuum tunnel between states, each bubble a potential cosmos. Emotionally, this evokes awe tinged with isolation, beings within a layer gazing outward, unaware of the enclosing shell, their memories part of a grander archive. In the reflective silence, the mystery coalesces. Gravastars, growing stranger. With each model, challenge the void's finality, proposing instead a cosmos alive with concealed worlds. The mimicking exteriors, the preserved interiors, the anomalies in data, all converge on a truth veiled in darkness. As the stare intensifies, the return gaze sharpens, revealing not emptiness, but the intricate weave of realities intertwined. The universe in its profound remembrance stares back, not as void but as veil. In the hushed depths of the cosmos, where the remnants of collapsed stars whisper secrets of ultimate fate, an enigmatic alternative emerges from the shadows of theory, a Gravastar, a gravitational vacuum star that defies the abyss of singularity. Born from the relentless grip of gravity, yet resisting the plunge into nothingness, this construct reimagines the endpoint of stellar demise not as an insatiable void, but as a resilient sphere, layered in mystery, where quantum whispers hold back the tide of collapse. As the universe expands its ancient narrative, the Gravastar stands as a sentinel, embodying the delicate balance between destruction and endurance, a cosmic artifact where the fabric of reality bends but does not break. At the heart of this vision lies the quantum vacuum core model, a framework etched in the mathematics of general relativity, fused with quantum insights, proposing a structure that averts the cataclysmic singularities plaguing black hole paradigms. Envision the interior as a realm of de Sitter space, a vast expanse infused with negative pressure, where energy density and pressure entwine in opposition. Pressure equaling the negative of density, a manifestation of dark energy's repulsive essence, echoing the cosmological constant that drives the universe's accelerating sprawl. This core, devoid of thermodynamic entropy, forms through a quantum phase transition during gravitational collapse, where the vacuum itself condenses, stabilizing against further implosion. Encircling this ethereal void is a thin shell, a boundary of ultra-dense matter, mere Planck lengths in thickness, composed of ultra-relativistic fluid where pressure matches density, a state of extreme stiffness that withstands the inward crush. This shell, poised at the precipice where an event horizon might form, instead replaces it, allowing no infinite blue shifts or trapped trajectories, its finite extent ensuring a global time coordinate threads through the entire structure. Beyond lies the exterior, a familiar Schwarzschild geometry, curving spacetime around an arbitrary mass, indistinguishable from a black hole at great distances, yet harboring no hidden horrors within. In this architecture, singularity is thwarted not by evasion, but by transformation. The quantum vacuum's negative pressure counters gravity's inexorable pull, maximizing entropy in the shell while preserving a regular spacetime, free from the pathologies of infinite curvature. The Gravastar, in its quiet defiance, emerges as the true terminus of collapse, a cold, compact sentinel where quantum effects orchestrate stability, reflecting the universe's reluctance to surrender to oblivion. Building upon this foundation, The model evolves into conceptions where the Gravastar's essence draws from the quantum realm's most profound collectives, the Bose-Einstein condensate, a state where matter, chilled to the brink of absolute zero, coalesces into a singular quantum entity. Here the collapsing stellar core undergoes a gravitational analog of this condensation, extending the principles of bosonic coherence to the gravitational field itself, transforming the interior into a macroscopic quantum superfluid. As temperatures plummet amid the crush, particles, or in this gravitational twist, vacuum modes, occupy the lowest energy state en masse, behaving not as disparate elements, but as a unified wave function, a coherent symphony defying classical fragmentation. This superfluid core, with its near-zero entropy, exhibits properties of a gravitational Bose-Einstein condensate, where quantum fluctuations stabilize the structure, preventing the descent into singularity through emergent repulsive forces akin to those in ultra-cold atomic gases. The thin shell in this view interfaces with the condensate, its ultra-dense composition reflecting incoming radiation with near-perfect efficiency, rendering the Gravastar a dark, mirror-like orb that scatters light back into the void, rather than devouring it eternally. Stability arises from the condensate's quantum nature. Small perturbations dissipate harmlessly, the wave-like behavior ensuring thermodynamic equilibrium without the instabilities of Hawking radiation or information loss. In cylindrical extensions of the model, this condensate endures even in asymmetric spacetimes, its superfluid properties adapting to maintain integrity, suggesting Gravastars could form in diverse cosmic scenarios, from stellar remnants to primordial collapses. The Gravastar, thus condensed, becomes a quantum beacon in the gravitational storm, its reflective surface a testament to the universe's capacity for order amid chaos, where the many dissolve into the one, enduring against the entropy's tide. Yet, the Gravastar's enigma deepens when viewed through the lens of holography, a principle that posits the universe's profound truths, encoded not in volumes but on surfaces, a cosmic projection where higher dimensional realities manifest in lower bounds. In this holographic Gravastar hypothesis, the thin shell emerges as more than a barrier. It becomes the canvas upon which the interior's entire informational content is inscribed, mirroring the holographic principle derived from black hole thermodynamics and extended through string theory's dualities. Drawing from the ADS-CFT correspondence, where gravitational dynamics in anti-de Sitter space equate to conformal field theories on its boundary, the Gravastar's surface encodes the quantum vacuum core's complexities. Every fluctuation and energy state projected outward in a two-dimensional script. This encoding resolves paradoxes of information preservation. As matter accretes, its essence imprints upon the shell, conserved in the holographic degrees of freedom, much like the entropy bounds that limit black hole information to horizon areas. The interior, with its de Sitter expanse, ties to string theory's brains and fluxes, where the holographic mapping ensures no loss in the transition from collapse to stability. The shell's tension, a physical manifestation of boundary conformal fields, speculatively, yet credibly within these frameworks. This holography extends to the Gravastar's role in cosmic thermodynamics, where the surface's entropy, arising from hydrodynamic fluctuations, aligns with Bekenstein-Hawking limits, yet without the evaporation dilemmas, suggesting a stable archive of stellar history etched eternally on the periphery. In this projection, the Gravastar transcends mere objecthood, becoming a holographic microcosm, where the vast interior's secrets unfold on a finite veil, reflecting the universe's own illusory depth, a philosophical echo of reality's layered illusions. As contemplation turns to the Gravastar's inner sanctum, theories of false vacuum and cosmic evolution unveil a tapestry of potential genesis, where the core's metastable state harbors the seeds of renewal. The interior, characterized by its dark energy-like negative pressure, embodies a false vacuum, a higher energy configuration, locally stable yet precarious, poised on the edge of decay to a lower true vacuum state. This metastability, drawn from quantum field theory, implies the core could tunnel through energy barriers, nucleating a bubble of true vacuum that expands at light speed, rewriting the local physics in a cascade of transformation. In Gravastar models, this false vacuum mimics the inflationary epoch of the early universe, its repulsive force not only stabilizing the structure, but potentially inflating outward if the shell yields, birthing an expanding realm within a new dimensional fold. Observations of cosmic microwave background anisotropies and large-scale structures hint at such vacuum dynamics, where our universe's dark energy may echo remnants of similar metastable phases. The Gravastars formation, violent and implosive, could thus serve as an engine of cosmic genesis. Collapsing matter plunges through the core, exploding into a nascent universe, its expansion driven by the released vacuum energy, consistent with Big Bang dynamics. This process, speculated in extensions of the model, positions black hole-like collapses as portals to multiversal proliferation, each Gravastar a quiescent precursor to branching realities. Gamma ray bursts, those fleeting cosmic beacons detected by observatories like Fermi, might signal such transitions, their intense emissions the harbingers of vacuum decay igniting new cosmic fires. In this evolutionary vista, the Gravastar transcends isolation, becoming a nexus where stellar death fuels universal birth, a cyclical whisper in the grand cosmic rhythm. From these threads emerges a speculative horizon. Every black hole reimagined as a Gravastar could cradle the womb of creation, its false vacuum core a latent forge for new universes. The death of stars, those luminous giants exhausting their fusion hearts, might not culminate in sterile voids but in fertile incubators, where gravitational collapse compresses matter into quantum seeds, germinating through vacuum fluctuations into expanding bubbles of spacetime. This birthing, propelled by the core's inflationary potential, could spawn child universes detached from our own, their physical constants subtly varied, contributing to the multiverse's infinite diversity. Dark energy's pervasive influence, measured in supernova redshifts and cosmic microwave patterns, might leak from such processes, energy exchanged via subtle radiation between parent and progeny realms. Credibly extending false vacuum theories, this implies a Darwinian cosmos, where viable universes proliferate from the remnants of stars, their genesis a testament to gravity's dual role as destroyer and creator. The Gravastar in this light stands as a cosmic midwife, its shell a membrane between endings and beginnings, where the entropy of collapse transmutes into the order of emergence. In philosophical reflection, Gravastars illuminate a profound truth. Reality never truly collapses. It transforms, reshaping the debris of one era into the foundation of another. Creation and destruction reveal themselves as identical acts, twin facets of an eternal process, where the implosion of stars seeds the expansion of worlds, entropy's arrow curving back upon itself in cosmic symmetry. This duality echoes through the universe's vast expanse, a mysterious harmony where voids harbor potential and the apparent end whispers of renewal, inviting eternal contemplation on the boundless cycle of being. In the veiled heart of the cosmos, where gravity bends the very essence of existence into impenetrable shadows, humanity's instruments strain to pierce the enigma of compact objects, those colossal remnants that challenge the boundaries between the known and the unknowable. The pursuit of verification unfolds as a solemn quest, not merely to observe, but to discern the true nature of these entities, whether they are the singular abysses predicted by classical theory or the exotic constructs born from quantum whispers. Gravitational vacuum stars that eschew the infinite densities of singularities for a stable vacuum core. These hypothetical forms, envisioned as spheres of de Sitter space-time encased in a thin shell of matter, emerge from efforts to reconcile the paradoxes of information loss and curvature extremes, proposing a universe where gravity's grip halts at a quantum boundary, rather than plunging into oblivion. As scientists refine their tools, each enhancement builds suspense, drawing ever closer to the horizon where distinctions might reveal themselves, inviting philosophical reflection on the limits of perception and the elusive truth woven into space-time's fabric. The array of telescopes synchronized across the globe, collectively forming a virtual instrument the size of Earth, stands poised for its next evolutionary leap, promising sharper visions of the supermassive entity at our galaxy's core. Recent observations have unveiled polarized light from this object, known as Sagittarius A, revealing magnetic fields spiraling like ethereal filaments around its edge, structures that hint at the dynamo powering relativistic jets and accretion flows. These images, captured in 2024, expose the interplay of plasma and gravity, where charged particles trace helical paths, their emissions polarized by the intense fields, offering clues to the spin and charge that might differentiate a classical horizon from a vacuum star's surface. Future campaigns, scheduled for annual expansions, incorporate higher frequencies at 345 GHz, enhancing resolution to probe finer details of the photon ring, the orbit where light bends eternally before escaping or falling inward. Such advancements, bolstered by additional stations in Africa, promise not static portraits but dynamic sequences, reconstructing the turbulent gas dynamics near the boundary with unprecedented fidelity, potentially capturing deviations in shadow size or brightness asymmetry that a vacuum star's reflective shell might impose. Speculatively, if this core object harbors a quantum-corrected structure, its image might betray subtle lensing effects or stability against collapse, contrasting the inexorable infall of traditional models. In this progression toward motion pictures of the galactic heart, one contemplates the mystery, a revelation that could affirm the seamless curvature of relativity or unveil quantum imprints, transforming our understanding of how the universe safeguards its secrets at the brink. As electromagnetic gazes sharpen, the symphony of space-time vibrations beckons with detectors attuned to the low-frequency murmurs of the cosmos. A space-based triad, envisioned as 3 spacecraft trailing in solar orbit, forms an immense interferometer, spanning millions of kilometers, sensitive to waves in the millihertz band, where supermassive mergers and exotic phenomena resonate. This instrument, designed to capture the inspiral and coalescence of colossal pairs, holds particular promise for detecting post-merger echoes, repetitive ripples that might arise from quantum modifications at the horizon, reflecting waves back into the void rather than absorbing them eternally. In theoretical explorations, such echoes could manifest if the boundary behaves as a partially reflective membrane, a hallmark of vacuum stars where quantum effects prevent singularity formation, potentially imprinting a series of delayed signals in the ring-down phase. Credibly extending these models, the detector's reach into the early universe's mergers might reveal discrepancies in waveform damping or frequency content, distinguishing the smooth absorption of classical horizons from the resonant bounces of quantum-corrected objects. Complementing this celestial vigilance, a ground-based successor with 40-kilometer arms emerges as a terrestrial colossus, engineered to probe higher frequencies with exquisite precision, capturing the full narrative of neutron star and black hole unions, including the chaotic post-merger oscillations that encode the remnant's internal structure. This explorer of the cosmic scale could discern subtle echoes in the ring-down, where overtones and mode mixing might betray a non-singular core, offering evidence for vacuum states that stabilize against infinite collapse. The suspense mounts in these detections, each wave a potential harbinger, rippling through space-time to whisper of boundaries that either devour or deflect, inviting reflection on the universe's reluctance to embrace infinities. Beneath the surface, in vast underground caverns chilled to suppress thermal noise. Arrays of neutrino telescopes scan the ethereal flux of particles that traverse the cosmos, unhindered by matter or fields. These detectors, immersed in cubic kilometers of ice or water, capture the rare interactions of high-energy messengers from distant cataclysms, seeking signatures of energy loss that might diverge from predictions for classical compact objects. In scenarios involving tidal disruptions, where stars venture too close to supermassive entities, the ensuing flares could accelerate particles to peta-electron-volt scales, producing neutrinos if the core is a voracious absorber, yet perhaps yielding different spectra, or missing fluxes if a vacuum star's shell alters the accretion dynamics. Speculatively, the evaporation process, driven by quantum tunneling near the boundary, might emit distinct particle cascades. Classical horizons predict a thermal spectrum of neutrinos diminishing over eons, while a vacuum star's stable configuration could suppress such radiation, manifesting as an absence of expected low-energy signals from primordial remnants. Recent analyses of ultra-high-energy events trace some to blazar jets or merging systems, but the quest intensifies for anomalies in missing energy, gaps in the balance of incoming and outgoing fluxes that hint at alternative interiors where quantum vacuum energy repels singularity formation. Philosophically, these ghostly traversers embody the universe's transparency, piercing veils that light cannot. Yet their silence in certain spectra might echo the deeper mystery of structures that preserve information without loss, a quiet testament to nature's aversion to paradoxes. Within the silicon realms of supercomputers, numerical simulations conjure the violent dances of merging compact objects, modeling the gravitational maelstroms that reshape spacetime. These digital crucibles replicate the inspiral, collision, and aftermath of pairs, contrasting the waveforms from classical horizons, where energy dissipates into a merged singularity, with those from vacuum stars, whose shells might introduce resonant frequencies or alter damping. In detailed runs, the light curves from accretion disks surrounding these entities reveal potential differences. A vacuum star's boundary could scatter photons with unique polarization patterns, twisting the emitted light in ways that betray a non-absorptive surface, while frequency shifts in the emitted waves might exhibit prolonged ringing absent in singular models. Magnetized scenarios further illuminate distinctions, as fields threading the merger amplify jets or outflows, with simulations showing how a stable vacuum core sustains stronger magnetic reconnection, yielding brighter electromagnetic counterparts or variant gravitational signals. Credibly, these computations predict observable divergences in the ring-down phase, where overtones dominate earlier for non-singular objects, offering templates for future detections to discriminate between the inexorable collapse and a quantum-stabilized equilibrium. As processors evolve, incorporating quantum effects into relativistic frameworks, they bridge the scales, simulating how vacuum fluctuations might inflate to form shell-like barriers, a speculative yet grounded pathway to resolving the information conundrum. In this virtual theater, the narrative of convergence unfolds with suspense, each iteration refining the lens through which we view the cosmic drama, prompting reflection on simulation as a mirror to reality's hidden codes. Deeper still, in the theoretical forge where relativity's smooth geometries meet quantum mechanics' discrete jitter, researchers labor to unify the forces, exploring how vacuum states might supplant singularities. Loop quantum gravity, a framework quantizing spacetime into granular loops, predicts that at Planck scales, curvature bounces rather than diverges, birthing structures akin to vacuum stars, where positive cosmological constant interiors repel collapse. These models, tested against black hole thermodynamics, suggest information encoding on quantum-corrected horizons, preserving unitarity without evaporation paradoxes. Experimental pursuits, from analog systems in laboratories to cosmological observations, probe these bridges, with recent proposals using entangled particles to mimic gravitational effects, hinting at emergent spacetime from quantum entanglement. Speculatively, such unification could reveal vacuum stars as natural outcomes, their de sitter cores echoing the universe's accelerating expansion, a philosophical symmetry linking microcosmic quanta to macrocosmic voids. Ambitions extend to proposed voyages and observatories. Like the conceptual mapper of black holes, a space telescope array designed to chart the innermost accretion flows and shadow silhouettes of numerous compact objects, measuring photon rings with precision to detect deviations from Kerr metrics that vacuum stars might exhibit. This mission, envisioned in long-term astrophysical visions, would spectroscopically probe masses and spins across quasar populations, seeking anomalies in reverberation mapping that signal alternative boundaries. Paralleling this, an underground triangular detector, the Einstein telescope, burrows into silence to capture gravitational waves from inspiraling pairs, mapping the fields around compact remnants with sensitivity to probe exotic populations, separated by mass and compactness. Its design, attuned to frequencies revealing tidal deformabilities and ring-down modes, could distinguish vacuum stars through waveform mismatches, exploring extreme gravity where quantum corrections surface. Together, these endeavors suspend the inquiry in anticipation, charting the gravitational landscapes that might affirm or refute the singular paradigm. Yet, amid this arsenal of ingenuity, a profound debate simmers. Will empirical scrutiny suffice to unmask the vacuum star, or does its mimicry of classical horizons render it an eternal specter, observable only in faith? Analyses of gravitational signals, like those from the 2019 event, have entertained vacuum star interpretations, with ring-down echoes potentially aligning, yet eluding definitive proof, as current data favors the simpler singular model. Shadow images, while excluding certain alternatives, leave room for indistinguishability, with theoretical shadows of vacuum stars mirroring those of horizons under specific conditions. Philosophically, this impasse evokes the limits of science, where nature's veils might conceal truths beyond direct gaze, compelling belief in quantum resolutions without empirical coronation. In this reflective stasis, the pursuit endures, a testament to humanity's dialogue with the cosmos, where verification dances on the edge of possibility, forever teasing the boundary between revelation and mystery. As the cosmic narrative draws toward its contemplative horizon, the narration slows, its cadence adopting a reflective, melancholic timbre, as if the universe itself pauses to whisper secrets long held in shadow. The vast expanse, once ablaze with the fury of creation, now yields to a quieter introspection, where the boundaries between end and renewal blur like ink diffusing in still water. Perhaps the universe abhors true voids. Perhaps it cannot bear the silence of infinity. So it creates illusions, masks over the face of death. In this veiled realm, the concept of the Gravastar emerges not as a mere astronomical curiosity, but as a profound metaphor for existence itself, challenging the inexorable pull toward oblivion. Conceived in theoretical explorations at the turn of the millennium, Gravastars, gravitational vacuum stars, arise as hypothetical alternatives to the enigmatic abysses known as black holes. Where traditional models depict a star's collapse culminating in a singularity, an infinitesimal point of infinite density where the laws of physics fracture, the Gravastar proposes a different fate. Drawing from solutions to the equations of general relativity, researchers have envisioned a structure where gravity's crush is halted not by an impenetrable horizon, but by a delicate equilibrium. At the core lies a region of de sitter space, a vacuum infused with negative pressure, akin to the repulsive force driving the universe's expansion, surrounded by a thin shell of exotic matter, fluid moving at relativistic speeds, its energy density balancing the inward tug. This shell, mere Planck lengths thick, forms a boundary where quantum effects conspire to prevent total collapse, creating a stable object that mimics the gravitational signature of a black hole without its paradoxes. The genesis of this idea stems from efforts to reconcile gravity with quantum mechanics, fields that clash at the extremes of density. Observations of stellar remnants, captured through gravitational wave detectors, merging signals from distant collisions, have painted pictures of compact objects whose masses and spins align with predictions, yet leave room for alternatives. In papers archived in scientific repositories, theorists have modeled these entities, incorporating modified gravitational frameworks to explore their stability. Recent analyses, building on foundational work, have examined how such structures might form under the influence of string-like clouds or altered curvature terms, revealing that gravastars could endure perturbations that would destabilize simpler models. Energy calculations show a configuration where entropy, a measure of disorder, is distributed across the shell, avoiding the information loss dilemma that plagues singularities, where details of infalling matter seem erased from the observable cosmos. Suspense builds in the contemplation of a star's demise, a cosmic drama unfolding over millennia. Imagine a massive star, its core depleted of fusion fuel after eons of forging heavier elements in thermonuclear fires. Gravity asserts dominance, compressing the remnant inward with relentless force. In the conventional narrative, this leads to a horizon from which no light escapes, a veil drawn over the interior's mysteries. But in the Gravastar hypothesis, the collapse halts at the brink. Quantum fluctuations, those ceaseless dances of virtual particles in the vacuum, amplify to form a phase transition, a metamorphosis where matter transforms into a condensate, its properties governed by Bose-Einstein statistics on gravitational scales. This shell, pulsating with ultra-relativistic energy, acts as a membrane reflecting incoming radiation in subtle ways that differ from the Hawking glow theorized for black holes. Speculatively, yet grounded in extensions of these models, such objects might emit gravitational waves with distinct ring-down modes, echoes detectable by future observatories, offering a testable distinction from their darker counterparts. Emotionally, this evokes a sense of hidden resilience, a universe that feigns surrender, only to reveal deeper layers of endurance. The Gravastar becomes emblematic of how endings conceal beginnings, a stellar phoenix cloaked in darkness. Just as a star's implosion births new forms, whether neutron-dense cores or these vacuum spheres, perhaps consciousness and matter follow suit. In biological realms, observed through evolutionary records etched in fossil strata, life adapts at the edge of extinction, complexity arising from crisis. Neural networks in living brains, firing in synaptic cascades, mirror this. Collapse of old pathways forges novel connections, memory reborn from apparent loss. Extending this credibly, the universe's fabric might weave similar patterns, where gravitational collapse spawns emergent structures, information preserved in holographic encodings on the shell's surface, much like theories proposing that black hole horizons project interior realities outward. Philosophically, the Gravastar invites reflection on the illusions of perception, the veils that obscure deeper truths. What humanity labels a black hole may merely mark the frontier of observation, a threshold where familiar physics yields to the unknown. Telescopes peering into galactic centers reveal supermassive entities devouring gas clouds, their accretion disks glowing with X-ray fury, yet the core remains shrouded. Light bends around these behemoths, as captured in silhouette images from global arrays of radio dishes, confirming immense gravity wells. But if Gravastars inhabit these shadows, their lack of a true horizon implies no irrevocable trap. Particles skirt the shell, their paths altered but not doomed. Light falters not from imprisonment, but because the interior beckons something beyond electromagnetic grasp. Perhaps gravitational whispers or quantum entanglements that transcend luminosity. This boundary then is not a tomb but a gateway, where reality conceals its profounder essence, much as quantum indeterminacy hides particle states until measured. Delving further into this mystery, consider the role of vacuum energy, that subtle hum pervading empty space, inferred from the universe's accelerating sprawl. In Gravastar interiors, this energy manifests as a positive cosmological constant, countering gravity's crush with outward push, a balance observed in cosmological data matching galaxy recession rates. Theoretical extensions posit nested Gravastars, layered like ancient dolls, each shell enclosing another in recursive stability, a solution to relativity's equations, suggesting infinite regress without singularity. Such configurations, explored in recent mathematical derivations, could arise from sequential collapses, each layer preserving information from prior states, a cosmic archive defying erasure. Speculatively, this mirrors multiversal ideas, where bubble universes spawn within others, each end birthing multiplicity. The emotional undercurrent deepens, a melancholic awe at nature's reluctance to yield to void. In the silence following a star's supernova outburst, waves of light and neutrinos racing across light years, the remnant lingers. A Gravastar perhaps, its surface a mirror reflecting the cosmos's gaze back upon itself. Consciousness, emerging from matter's complexity as seen in neural evolution from simple organisms to sentient beings, might echo this. Minds collapsing under entropy's weight, yet reforming in collective memory or digital echoes. The universe, in crafting such illusions, affirms a philosophical tenacity, death as masquerade, infinity's silence broken by subtle harmonies. As reflections cascade, the Gravastar's metaphor expands to encompass the human condition. Perceptions of finality, drawn from life's cycles, seasons turning, civilizations rising and falling, reveal concealed renewals. Rivers carve canyons only to nourish valleys. Forests burn to seed rebirth. In stellar terms, observed through spectra of distant nebulae where elements recycle into new generations, this cycle persists on grand scales. Gravastars, if real, embody this. Gravity's apparent victory halted by quantum guardianship, stability forged from brinkmanship. The philosophical lens sharpens on observation's limits. Human instruments, from particle colliders recreating early cosmic conditions to space probes sampling interstellar dust, probe reality's edges, yet falter at singularity's predicted infinities. Gravastars resolve this by eschewing extremes, their structures finite, calculable. Light's failure to escape becomes a transition, not trap, perhaps to realms where other forces dominate, speculative dimensions curled in string-like geometries, waiting beyond luminosity's reach. In this contemplative expanse, emotion swells like a tide under moonlight, mourning perceived losses while embracing hidden potentials. The universe, through Gravastars, whispers of immortality disguised as end. Somewhere at the edge of a dying star, gravity has chosen not to consume itself. It has become still, silent, pretending to be gone. But within that quiet surface, the universe may be dreaming of itself, of rebirth, of all the light yet to come. The Gravastar is not the end of a star. It is the universe remembering that nothing truly dies. To deepen this philosophical repose, linger on the Gravastar's theoretical underpinnings, drawn from relativity's curved spacetime. Equations describe how mass warps geometry, light following geodesics bent into loops. In black holes, these paths spiral inward eternally. In Gravastars, they graze the shell, scattering with modified spectra. Recent models incorporate quantum corrections, stabilizing the configuration against collapse, entropy balanced across layers. Speculatively, Gravastars might seed galaxy formation, their stability influencing dark matter halos inferred from rotational curves. Observations of merging pairs, waves rippling spacetime, could distinguish via waveform tails, subtle deviations from standard chirps. Emotionally, This evokes wonder at nature's ingenuity. Voids filled with veiled vitality. Consciousness parallels. Thoughts collapsing into sleep. Awakening renewed, matter's patterns enduring. Perception's boundary extends to cosmic horizons, where expansion hides distant realms. Gravastars symbolize this. Observable mimicry masking interior novelty, light yielding to profounder senses. The metaphor culminates in existence's resilience, ends as illusions, beginnings eternal.